Now we are going to talk about how to get from displacements to strains. Okay, so let's get to it. Just like forces are represented by stress field, we represent deformation by displacement field. Okay, three functions representing the magnitude and direction of displacement of each point. Okay, looks like this. U of XYZ is UI plus Vj plus Wk. So this is, if you remember your fluid mechanics, we had velocity field. In solid mechanics, we have displacement field. Okay, so the analogy is fluid mechanics between velocity field and displacement field. That's what we are. Okay, so let's look at a particular example rather than in the abstract. Let's look at what happens when I'm thinking about bending. So uxy is minus k times xy, some function of xyz. Vxy is kx squared over 2. W is 0. So how can I look at this and figure out that it is actually bending? Well, let's draw it. Let's draw like what we would do for fluid mechanics. We will draw displacement field vectors, arrows, and we'll see what it looks like. There you go. If I took these things and drew arrows, this is what it looks like. Can you see that it is bending? Look at all the tips of the arrows. The tips of the arrows show us the bent shape. If you actually connect up all the tips, you will get a bent shape. Can you see that? If I connect up all the tails, I'll get this rectangle. I'll connect up all the tips, I'll get a bent shape. So this displacement can represent all kinds of shape changes. Okay, that is the whole idea. Okay, now I'm not just saying this for a casual thing. Here's from a paper on earthquake engineering, actually soil mechanics, where they're looking at what happens to a fault in in an earthquake. You can see the fault here. Can you see this? Can you see the displacements? How the earth is moving on one side and how the earth is moving on the other side? Can you see that this side is going to go up? This side is going to go down. So it's actually, some parts are going up, some parts are going down, and there's a surface where there's slip, and that is the fault. That's where the fault happens. And depending upon what's the friction coefficient, sometimes it will slip, sometimes it will lock. That is why it takes, whenever it releases the slip, that's when you get earthquake. That is how it works. Okay, so displacement fields are commonly used for representing all kinds of phenomena. Okay, very good. Okay, this displacement causes chunks of material to stretch and shear, resulting in local strains. We need to quantify this. How do displacements cause shape change? Just as forces were obtained from force intensity vectors by integration, strains will be obtained from displacement field by differentiation. The final result is easy to use and doable, very easy, but derivation is a bit painful because it combines geometry and calculus. We're going to plunge into it. We're going to learn how to do this, but you have to be prepared for some serious, differential calculus. So let's plunge into it. Okay, so we can use calculus for computing the strains from the displacement fields. So let's start. We're going to do it 2D. So consider the red dot in the figure and the two line elements OA and OB of the grid. Can you see that grid and the two line elements and the red dot there? So we're going to focus on that. The displacement field causes it to deform. I get these two green arrows. Okay, so OAB becomes O prime, A prime, B prime. We want to quantify how these things go depending upon the displacement field. So what we are going to do is we are going to blow it up. OAB becomes this OAB here large with the red dot. O prime, A prime, B prime becomes this purple dot with those two red wings. Okay. Now we are going to do some calculus, and you can see the distance between the red point and the purple point is the displacement U and V. If I want to find the displacement between B and B prime, then I have to do some calculus because the distance moved here is dy and all that. That's where we are. Okay, so what we want to do to measure the strain is first we remove this displacement. So we redraw our original thing as if it started at O. We just move it. So now you can see that if I look at the OA vector, O prime A prime vector is longer at this at an angle, right? OB vector is vertical, O prime B prime is longer at an angle. So we want to calculate how much longer and at what angle. Okay. So you do a little bit of calculus. Basically, we expand. We know that if this is UV, this tip will be U plus DU, V plus DV. So, and I know that DU is DU dx dx and DV is DV dx dx. So what happens is the axial strain is very simple. O prime A prime minus OA divided by OA. If you do that, you will find that it's just this blue arrow, DU dx. Right? Same thing. Rotation is gamma x. That angle, that little angle there is called gamma x. And that is dV dx. I'm sorry, it says du dx. That's not correct. That should be dV dx, the green stuff. Okay. Now you repeat that for the other direction. The vertical distance, this blue arrow is given by this blue dV dy. And then this angle is given by du dy. Can you see du dy divided du dy dy divided by dy will give you tan of this angle. And tan angle is equal to the angle for small angles. That is why we write approximate. Okay. So now I know this angle and this angle. So total change in angle is the sum of these two things. So if a total change in angle is gamma xy, is gamma x plus gamma y, dv dx plus du dy. So the sum of these two green terms will give you the total angle change. The blue terms will give you the axial strains. Okay, you can stare at it. My suggestion is you try to derive all of these things yourself. Then you will see what is happening. Okay, otherwise you won't understand exactly how this goes. For the purposes of FEA, even if you don't understand, you can still use it. But you have to understand the meaning of this. So what it is that the most important thing to know is what is this axial strain along the x-axis? Change in length per original length along the x-axis. That is O prime A prime divided by OA, O prime B prime divided by OB, and the angle between them. So that is what it means. Okay. In 3D, you focus on a point O, like shown here. We want the strain there. Okay. What happens is it moves to this new point O prime. So change in length per unit length in the original x direction, epsilon x is du dx. For the y direction, epsilon y is approximately du dy. Epsilon z is approximately dw dz. Very nice. Then change in angle, this gamma xy is du dy plus dv dx. Gamma y xz is du dz plus dw dx. And gamma yz is dv dz plus dw dy. There are the 6 things that we are doing, all of it in terms of derivatives with respect to u. And what we do is we write it in a compact way. Right? So we write your displacement as a vector, u, v, w, and then we try to do an operator on that vector to give the six components of the string. This operator is called the b hat. The hat to ensure that you're not doing matrix multiplication, but you're actually doing operation like gradient. So you're writing gamma equal to b hat of u. Okay, this is the compact notation for it. So b hat is the strain operator, just like gradient operator, and it will give you the strain when the displacements are known. Okay, thank you very much. We will actually do an example problem and then we will see what happens next. Okay, here is an example problem. So for pure bending again, we know uxy is minus kxy, vxy is kx squared over 2, w is 0. Let's see what happens. So the strain is a b hat of u. So I want you to do it by yourself and tell me what you get for the strain. So pause the video, try and do this operation, and compare with what I got. That is the best way to learn. Okay, it will take you only 2 minutes, but if you get used to it, then you'll see how it works. Did you pause? Did you come? Do you have your answer? It should be fairly easy. Let's see what I get. So basic idea is to do like matrix multiplication, but instead of multiplying, we are operating. So let's look at the first row times the first column. First row times the column. So you get ddx of minus kxy, 0 times kx squared over 2, 0 times 0. So that's why I get minus ky if I differentiate with respect to x. Let us look at second row, first column, and I get 0 plus dkx squared over 2 dy plus 0. That gives me 0, and so on. You can see that I have only one strain component minus kxy. Okay, does that make sense? Well, we want the strain to be linear along the y direction as expected. Compressive strains on top, tensile strains on bottom. That's why there's a negative sign. That's it. We are done. So notice that the strain calculation is fairly simple. All you have to remember is this B operator. Okay. Once you do that, then it's easy. Thank you very much. We are done with this portion.